I like recording videos that can be used for other semesters. So here's the lecture part of Class 5 for ES211, Kinematics of Particles. Here we're dealing with polar coordinates. All right, so we dealt with path coordinates in the previous class, where we took a coordinate system that was based on the tangent to the path, which of course means that the one of the coordinates, one of the unit vectors, is aligned with the velocity, because velocity is always tangent to the path. So it's really convenient to choose that as being one of the coordinates, and then the other coordinate was perpendicular to it. So it was the normal coordinate, normal being perpendicular, and pointing towards the center of curvature, and along that line is where centrifugal acceleration takes place. But now we have another coordinate system that we can use. Most often we'll call it polar coordinates, but the book calls it radial and transverse. And the idea here is that we have a unit vector that's aligned with a particular point, right? A stationary point, or it could be a stationary point, and that's pointing from that stationary point towards the particle, right? So you could think of it down here from what we're seeing right here. You can see that this is the point on this coordinate axis that's selected as this reference point, and we have a position vector that's oriented from that point to the particle, and we call that position vector RP with respect to O, where the P is the particle and O is the origin right here. And the unit vector we choose is this E with a subscript R, and then the little caret hat right here. So that position vector could be fully defined by a magnitude of this radius, little r right here, and that position vector. And you don't actually need to have this next one right here, but you could conceptually think that maybe there was a angle vector that would be the magnitude of the angle, and then with this unit vector right here. This isn't too important to us right now. In fact, I think we could actually kind of like leave it out for the time being. All we need to do to be able to define the position is have the radial position vector and the magnitude, because that radial position vector is oriented at the theta position. Now, by doing this, we kind of give ourselves a little bit of a complication, because if you recall back to class 3, when we took the derivative of a vector, we had to use the product rule all the way through. So we had to take the derivative of every single part of the thing, and we demonstrated with rectangular coordinates that the consequences of that weren't important, because I and j, those unit vectors don't change with respect to time. But this ER that we've just introduced, this thing will change its orientation with time, assuming this is dynamics and the thing is moving, right? So we set this thing up right here by taking two different points, P and then P prime. The P prime has been a position that has happened after this thing has moved a certain amount over a certain increment of time. And we see that there is a theta and a theta plus delta theta change in this position. There's also a change in the length of the R. So two things have changed, the length of R and theta. Well, if we know whether velocity is going to be the time derivative of that position vector as we defined it, and using the chain rule, we have dr dt. Okay, so that really represents the amount of change that has happened in the radial direction, how far it has moved away from that center. But also, we have to take the change in angle that has occurred because of this change of orientation. So it's that original r times der dt. And that thing has changed. And another way of writing it would be maybe to put just a dot on top of that er dot. And so now we need to figure out, how do we find er dot? Well, one way about doing it is to say superimpose what happens with these vectors, with these unit vectors on top of each other, right? To collect them. So if we take this ER right there, and we put the ER prime right next to it, right here. So we have these two right here. We'll see there in order to make the equation, right, that we would say that ER prime is going to be equal to ER plus some change in ER, right? And then we could close the loop. One thing that's really important as we're looking through that is look what direction that is that thing is pointing, right? As excuse me, that's for a particular delta theta. As that delta theta gets smaller and smaller, we could see that ER begins to point in the same direction as the E theta. So the limit as that ER, the limit of that change in ER as we get smaller and smaller increments of theta, we could see that it starts to converge to be in the E theta direction. So the angle derivative, not the time derivative, but the angular derivative of ER is E theta. We'll also note in the other one, if we now instead take this E theta and then the new E theta dash there, we could see that now this thing, the delta E theta that we have right here, it starts to point in the negative ER direction. So as that theta gets smaller and smaller, that increment of that we've taken right here, is that starts getting smaller, that starts getting smaller, and we start, I guess I'm pointing the wrong way, it starts pointing this direction, which you'll notice is the negative ER direction. Now we can apply the chain rule right here, and we will find that d ER d theta, which is what we've just established up here, that's that thing, that we can take, if we want to get this instead to be, right, because we're looking for, on this previous page, we're looking for this right here instead. But right now, we have it in terms of d theta. So what we want to do is go d theta dt. You look at that right here, right? And now these guys cross out, and we're getting the thing that we want. So what we had to do in order to get this into something that was desirable, we had to multiply it by theta dot, which is that d theta dt right here, right? And we already know that right there turns into E theta. So the answer to this right here is that's equal to theta dot E theta. That's the proof of it. A similar thing down here, we might also need to know what happens with this other guy, right? This one right here. Well, if we want, we take d E theta d theta right here, and also multiply it by d theta dt. Thetas would cancel out, and you would get d theta dt, which is the thing that could be desirable. So what we find right here is we have, remember, we're replacing this with that, we get negative theta dot ER. I do that right? Sure. It's negatives pointing towards the R direction. It's pointing in the negative R direction, so it's pointing towards the center. Okay, so this is going to be useful later on. But this guy right here, we fix what was on the previous page, and we just say R dot ER plus R theta dot E theta. So we have two components of velocity. One of them is the radial direction getting longer, and one of them is going to be, so that would be like in that direction, right? This is the r dot. This thing, you could imagine this thing getting longer and longer and extending. But also we have the turning part of it, which is actually going to give a velocity component that's perpendicular to r, and that's going to be r theta dot. So the combination of those two things, the thing getting longer and the thing spinning, can be represented for the velocity in that way. Now, if we want to go ahead and do the same thing for the next, for the acceleration, remember that we're going to take the time derivative of, so we're going to have d dt out here. It's easy to write this on a piece of paper, but I'll do it right here. We're going to take r, okay, this right here, r dot er plus r theta dot E theta, right? Well, I don't need that. So now we have to make sure that we take the derivative of every one of these things. We're going to use the product rule for everything here. So starting off right here, time derivative E is going to be of r dot is r double dot. All right, so then we take an r dot and we take the time derivative of ER. We've already established that that is going to be right here. The time derivative is theta dot E theta. So that when we take the derivative of ER, we have theta dot E theta. So we're now going on to the next one. You'll notice there's three parts to this. So we go plus, start out with the first one, r dot theta dot E theta. Now we go to the next one. Go plus r theta double dot E theta. And lastly we go r theta dot. Take a look. We want to take the time derivative of E theta, which we previously already said the time derivative of E theta was negative ER. So we go negative, whoop, excuse me, I messed up. What? One back. Sorry, not this one. I don't mean that one. I mean this one right here. Right? E theta dot is going to be negative theta dot ER. Negative theta dot ER. So negative theta dot ER. Collect all these things up, and we find that the acceleration is going to be, okay, well, we start off when we see in ER, we have R double dot. These are E theta, E theta, E theta. Now we got the ER. We notice that it's going to be negative theta dot squared R, or I think we generally are going to write this as a negative R theta dot squared, and that's the ER. We take a look at here. We see an r dot theta dot and an r dot theta dot. So there's two of those. Generally, we make that the second part of this. We look over here for the other E theta. We have r theta double dot. And then we have these two right here of those. So there's two of these parts. And there you go. We have an acceleration. And it has four parts. Two components, and each of them has like a physical meaning that we should really take a look at. First off, similar to the the r dot, we have the fact that this thing could be getting longer and longer, but it could be accelerating. It could get very, very fast, r double dot. It could be increasing its speed as it gets longer and longer. The rate at which it gets longer is increasing. So that's an r double dot. We also have the second cousin, and it really is the same thing, as our centrifugal acceleration. Remember that in the centrifugal acceleration, was v squared over rho. Okay, so another way that you could, that you could find, remember that that velocity is tangent to the path. Well, if it's a circular path onto the thing, let me see if we could find this down here. Right here is the velocity, right? If r doesn't change, here's what the velocity is that's going to be tangent to the circular path. That r theta dot could be the velocity right in there. So if we were to like stick in that v is equal to r theta dot right into there, and remember that in this case that rho becomes r right here, what we would find is you'd have r squared theta dot squared over r. One of the r's would cancel out here, and we would have r theta dot squared. Right? So these two things are really like related to each other. And if you take a look at this right here, you'll notice that it's negative, so it has a component of acceleration, if that's the particle, that's pointing downwards towards the center of curvature. That right here is another way of writing out centrifugal acceleration. We also have over here in the theta direction, we also have the possibility that this thing is spinning faster and faster. So in terms of an acceleration that might be coming out right there, we have in that direction, we have this r theta double dot. Now the next one is the most curious of the accelerations, and it actually is a physical phenomena, and it's got a name. This right here is Coriolis. I'm probably spelling this wrong. Maybe there's two L's? Let's try it, two L's. Coriolis acceleration. It's a combination of having r dot and theta dot. So if I sometimes will draw this as being on a let's say one of those merry-go-rounds. Remember those merry-go-rounds that you were on as a kid? You know, they had the little handle things that look like that right there, and you would spin them around. Well, if you were on this and you were walking outwards onto the thing, let's say it's a really big one and it's spinning, it doesn't need to accelerate. And you don't need to accelerate. All you need to do is walk outwards or walk inwards, and you're going to feel this kind of push over to the side. That's sort of like this, sometimes they refer to it as this magic hand, and that's Coriolis acceleration. It's an interesting phenomenon, but it also shows up right here inside our polar coordinates acceleration. So these are like summaries of the equations that they're putting out there. Here is what the velocity vector looks like in polar coordinates with the r dot and the r theta dot. Here's the acceleration with these four individual things, r double dot minus r theta dot squared. Remember that this is the centrifugal acceleration. Then we have r theta double dot. Right, so the angular velocity is increasing, so that has a consequence. And then we have this crazy Coriolis acceleration that are part of this. So I have this cartoon. It's supposed to be kind of help you to, I don't know, visualize the usefulness or what scenario, maybe a scenario where this might occur. And so just think of this fishing line as being the R, right? That's the R. Well, that fishing line can increase R dot, the speed at which it's going out, but it can also even increase, the speed can increase. So you could have R double dot that's going on right there. We could also spin, so we can have an angular position, but we could also have an angular velocity, and we could have an angular acceleration. So, and what we're really trying to do, we're in kinematics, so we're trying to describe the motion of this particle and trying to fully describe it in a systematic way. So these polar coordinates can be useful. And why would we want to choose to use them? Well, some motions just lend themselves to this coordinate system. They're just because you can best describe the motion of the particle by referencing a central point and the distance from that central point and from the angular position from as the thing is moving along right there. Just like in this chair right here. This would be a polar coordinate opportunity. That it's easier to describe the motion in these terms. You could still do it in x and y terms. So you could do I and j as part of this. You could also do it in path coordinates. That's totally valid. It's just that sometimes it's more convenient to use a particular coordinate system. So that's where the main part, the core of the lecture ends. And let's see how long that took. It's interesting to me to see how long. That was 20 minutes. Maybe I should make it shorter. I think I said all the things I needed to say, though. So, look at Edge Keeper.